In lesson 8, it is titled Sine and Cosine in the Same Right Triangle. So we're going to be looking at sine and cosine within the same right triangles. So go ahead and turn your book to page 171. That's where we're going to start. And so in this first activity, it's which one doesn't belong. So just pause the video, pick which one you choose that doesn't belong, and then come back to the video. So as always, there are various reasons that each of these don't belong. So there isn't one right or wrong answer, but here are some answers that you might have come up with. Maybe you said A doesn't belong because you can use cosine directly to solve for X. You could set up a cosine function here. B doesn't belong because it has a Y instead of an X. Or because you can use tangent to solve it. It's the only one you can use tangent directly for. Maybe C doesn't belong because it's not a right triangle and it doesn't have a horizontal side. So those could have been two options for C. And for D, it only has just the right angle measured. And the variable isn't on the shortest side. So in every other one, the variable was on the shortest side. So again, just a couple options. If you had something else, that's fine. On this next activity on page 172, so if you have access to a partner, do this with a partner. So one of you solve column A and the other one solve column B. So if you're in class, you could do that with somebody next to you. If you're doing this remotely, either phone a friend, text somebody, which one are you going to do? And you can do column 1 or partner 1 or partner 2. I am going to put up answers for both. So if you're working on this alone, you can just choose one column and then you'll be able to compare to the other set of answers. So go ahead, pause the video and work on those 3 problems, then come back. So in this activity, you were setting up trig functions for each of these. So I'm going to set it up for these first 2 problems. So remember that you'd be using your calculator for this and your reference chart. So your reference chart will tell you about cosine, sine, and tangent and those ratios. So the first idea here is that you're figuring out the angle. Okay, so what's the acute angle you have? Then labeling the sides accordingly. Okay, so in this first one, the side across from the 90-degree angle is the hypotenuse. And then the side next to your acute angle, the 7 here, is the adjacent side. So the function that connects hypotenuse and adjacent is a cosine function. So you would be doing cosine of 41 is equal to the adjacent side 7 over the hypotenuse x. Then using your calculator to determine the decimal version of cosine of 41 and using cross multiplication to solve. So cosine of 41 is 0.7547 equals 7 over x. Then you can make it into a proportion, cross multiply. So you would get 0.7547x equals 7. Remember to get rid of this decimal that's being multiplied by the x, we would divide by it. So divide both sides by 0.7547. So 7 divided by 0.7547 is about 9.3. So that's what we would get for the hypotenuse in part A. So if you were doing the B column, the partner 2 column, a similar story, you would find your angle, identify your sides. So the hypotenuse is across from the 90. So the hypotenuse in this one is X. The opposite side, the side across from the 49 here, is the opposite. That's where your 7 is. So the function that connects the opposite and the hypotenuse is a sine function. So you would do sine of 49 equals the opposite 7 over the hypotenuse, x. You would type in sine of 49 into your calculator and get 0.7547 equals 7 over x. Create that into a proportion so you can cross multiply. So 0.7547x equals 7. Divide to get rid of this decimal. And you'll end up with x equals about 9.3. Yeah, 9.3. I wrote that wrong on the other side here. This is just supposed to be 9.3. All right, so that's kind of how you do each problem. So let me just give you kind of the equations and the answers here for the 3 so you can check them. Okay, so this is the function you should have set up for each of these. Here's the function you should have set up for each of the B's. And then the answer that you should have gotten. So go ahead, check your work, fix any mistakes. All right, so let's discuss what you were supposed to notice here. So here's those 6 problems. Okay, hopefully you have them written in your book too that you can be looking at. Okay, so what equations did you use? Okay, so it looks like we used sine and cosine in all of them. And then what did you notice? Okay, did you think back to any conjectures that we've done before? Because you likely noticed when I was solving, we ended up with the same decimal here, even though our function was different. So partner A typed in cosine 41, got 0.7547. Partner 2 typed in sine 49, okay, and got 0.7547. So can we think of any conjectures about our right triangle table here? And remember, we talked about sine and cosine of complementary angles were the same. Okay, so we noticed those kind of flipping in our table. And so what actually happens here, like let's write that in a general sense of the term. So mathematicians often use Greek letters. Okay, so think about like sororities if you've seen those. Theta is one of the main ones that mathematicians use. Okay, they also use letters like alpha, beta, phi, gamma. Okay, those are just a couple different ones. I would say the main ones that mathematicians, especially in geometry, use are theta, alpha, and beta. But so if you see those, they're just representing angles. So those would be in the angle measures versus side lengths are going to be the standard American alphabet. So let's write a conjecture for this in generic terms. Okay, so how do we say that sine and cosine of complementary angles are equal to each other? So let's write out sine. Okay, so sine of some angle, so let's call it theta, again, just like a variable. Now that's going to equal cosine of a complementary angle. So we want to be able to write the complementary angle here, complementary to this. So what does complementary mean? It means that the two angles total 90 degrees. So if this angle is 10, the complement is 90 minus 10 or 80. If the angle is 20, the complement is 90 minus 20 or 70. So if we now have theta here, it would make sense then that we would take 90 and subtract whatever theta is. This is our complement. Okay, so we'll put this in as the angle into cosine. So this equation here says that the sine of an angle equals the cosine of its complement. Or you could do this vice versa, and you could say cosine of an angle equals the sine of its complement. So let's take a look. So turn the page or go to page 173. And we're going to try and write a proof for this. Okay, so you're going to generalize that. Why does that work? Why is it seeming to work? Why will it always work? So draw a diagram there to help you. In number 1, labeling the sides and the angles. Okay, and then so pause, try to draw a picture, and then come back and I'll help you. So we'd want to have some of these measures, all this stuff really labeled. So I'm going to put theta here. So if this angle is theta and this one is 90, by triangle sum theorem, okay, which is that they total 180, we could subtract them. So 180 minus this 90 gives us 90. Then we need to subtract off the theta, so this is what's left. So this angle right here is 90 minus theta. So then let's label the sides. So across from the 90, the hypotenuse I'll label with an X. Across from the angle, okay, so across from theta, I'm going to call that side Y. And next to the theta, I'm going to call that X. So can you write out the sine and cosine in general from this picture? Because there's really no numbers here except for the 90-degree angle. So think about writing out sine of theta. So remember, sine is the opposite side over the hypotenuse. So what's the opposite side in this picture? Opposite is Y. Hypotenuse is H. Okay, so there's just the generic sign for this picture. So now let's do the cosine of 90 minus theta. Okay, because that's the other piece here. Okay, so we just did this. Now let's take a look at the cosine of 90 minus theta. So remember, cosine is adjacent divided by hypotenuse. So the adjacent side to theta is the X, or sorry, to theta. I want to do theta, 90 minus theta. My fault. Okay, so 90 minus theta, here's our angle. Adjacent to 90 minus theta is the Y. And the hypotenuse is still H. So the cosine of this angle here, this 90 minus theta, is also Y over H. So notice that those are the same, the division of the same two sides. So then you just want to try and write that out in a proof. Remember, that's kind of writing it out in a sentence, explaining your reasoning and kind of what you did. So try and write this out, what we just did in sentences. Okay, so write out your first draft. Then if you're in class, compare it to somebody next to you, or phone a friend if you're remote learning. Okay, have somebody send you a picture of what they wrote so you can compare and you send yours. Then come back to the video and check this sample response. So here's a sample response. I just kind of did it in bullet points of like each different thing versus writing it into a paragraph. So this is just saying in a right triangle, we're going to have angles 90 and theta. That's how we started. Then we labeled the sides. Hypotenuse is across from the 90. I labeled the one across from theta Y and next to theta X. So the sine of that is opposite Y over hypotenuse H. Okay, so we came up with the sine. Then triangle sum theorem gave us this other angle here as 90 minus theta. So we did the cosine of that angle, which was adjacent Y over hypotenuse H. We see that those two are equal to each other. Okay, so sine of theta is Y over H, cosine of, oops, that should say 90 minus theta. Okay, so that should say 90 minus theta in there. Okay, so the cosine of 90 minus theta is Y over H. Therefore, Sine of theta and cosine of 90 minus theta are equal to each other. All right, then let's take a look at some of this. So you can kind of write this at the bottom of page 173 or at the top of page 174. You can cross out that "Are you ready for more?" and kind of write down a couple of these ideas or think about this. So let's take a look at these three triangles. So what I want you to do is see if you can match these three equations to these triangle cases. So thinking about sine of theta versus cosine of theta. When would the sine, which is opposite over hypotenuse, be less than the cosine, which is adjacent over hypotenuse? When would they be equal, and when would sine be bigger than cosine? So pause the screen, see if you can think about where those are going to match up, then come back. All right, so if we take a look, okay, the hypotenuse in each case will stay the same, right? The hypotenuse doesn't change. So we're taking a look at the opposite side divided by the hypotenuse versus the adjacent side. So if we want it to be a bigger number, we want or in this case, we want it smaller. So we want the opposite side to be smaller for the sine to be smaller. So in this case, opposite over hypotenuse is going to be smaller than adjacent over hypotenuse. Okay, so this one matches with the first triangle here. Okay, then the next one, when would they be equal? Well, they'd be equal when the two sides, the legs, are the same, so that the opposite is the same as the adjacent. So that's going to be in this one. So number 3 would be, we want the opposite to be bigger so that the sine is bigger, so that fraction is bigger. So here we see that the opposite side, okay, opposite of the theta, this is bigger than the adjacent, so the sine is going to be bigger here. So if we relate that back to what we just talked about here, where we know that sine and cosine of complements are the same, what kind of angle measures would produce this? So we see it here, what will produce them being equal, because the legs would have to be equal. So these complements would have to be the same angle. So 90 divided by 2. Okay, so 45. So if theta is exactly 45, then the two sines and cosines will be the same. So what would give us this one where we have a sine that's smaller? So compare these two angles. So in order to get this short side, or this side to be short across from the angle, this has to be a small angle, right? So this has to be small in comparison to the 45. So for sine to be smaller than cosine, theta needs to be less than 45. So then the opposite of that, when would sine be bigger than cosine? If the angle is larger than 45. So here's your lesson summary. So what we're talking about is within the same right triangle. Okay, if you do the cosine and sine of complements, remember it's going to be equal. So the cosine of 25 is going to equal the sine of 65 because they're complementary. And vice versa, the cosine of 65 is the same as the sine of 25. So if I said something like this, if I said that, what does the sine of 30 equal? The sine of 30 is going to be equal to the cosine of 60 because these are equal to 90. Okay, so if your angles are complementary, the sine of one equals the cosine of the other. And then we talked about that in general terms, okay, using theta instead of an actual angle measure. So we put a theta in. So the sine of theta is y over h. So the cosine of the other angle is going to be y over h. Okay, so you see the sine and cosine up here. So cosine of theta would equal sine of 90 minus theta. Cosine of 90 minus theta would equal sine of theta. So if you wanted to like write that out in a sentence instead of all of these symbols, what that's saying is cosine of an angle equals sine of the angle's complement. Okay, and vice versa. Sine of an angle equals the cosine of the angle's complement, meaning the angle that adds to 90 with it.